So this is a warm-up that I would normally give you at the very beginning of a class period to do. So we're just going to run through these together. The prompt is to write the Lewis structures for the following compounds. So we have CH4 as our first compound. Remember, when we look at Lewis structures, the first step is to add up all of the valence electrons that are contributed from each element. So carbon is in column 4, so it's going to contribute 4 electrons. Hydrogen is in column 1, but remember there are 4 in this formula, so we have to take that into account. This gives us a total of 8 electrons that need to be distributed throughout this compound. We're going to put carbon in the middle, because remember the only thing we can do with hydrogen is put it around the outside of another element. And in doing this, we need to bond the carbon to each hydrogen. So each of these bonds requires 2 electrons. So we have 2, 4, 6, 8. And I've used up all of my electrons in doing this. So the final Lewis structure looks like this. CH4. Now H2O. We want to look at hydrogen, which is in column 1. There are 2 of them. And then we're adding that to what oxygen contributes. It's in column 6, so it contributes 6 valence electrons. This, again, gives us a total of 8 electrons. At this point, we're going to do the same thing we did before. We're going to put oxygen in the middle, and we're going to put a hydrogen on either side. And we have to bond them, so we're going to use 4 electrons total to bond each hydrogen to an oxygen. So this means starting from 8, we're subtracting 4, and we have 4 left over. They don't want to go to hydrogen. Hydrogen's duet rule is already satisfied. So rather than putting them on hydrogen, we're going to put 4 electrons on oxygen. We're not binding them to anything else at this point. We're just using what's called a lone pair to do this. So this is a bonding pair. Obviously the one involved with the bonding. The ones by themselves are what's referred to as a lone pair. So this would be the acceptable Lewis structure for water. NH3, nitrogen is in column 5, 5 electrons in the outer shell. We're adding that to hydrogen's contribution of 1 times 3. So this, again, is a total of 8. You're probably noticing a pattern here, and what we're doing is showing you all of the different conformations involving 8 electrons to be distributed. Nitrogen in the center, and remember we put nitrogen in the center because only hydrogen can go around the outside. So our first step is to bond all of the elements, which is what we've done here. We used 6 electrons to do that. So 8 minus 6 is 2. I have 2 left over. They cannot go on any of the hydrogen atoms. They can only go on the nitrogen. So we have 3 bonding pairs, 1 lone or 1 non-bonding pair. If you're following along and doing the homework, the next question was on the basis of the electronegativity values given in the figure that you were provided. Indicate whether each of the following bonds would be expected to be ionic, covalent, or polar covalent. So here all we're doing is looking at the difference between the electronegativity values for the 2 elements that are listed. For A, hydrogen is 2.1. So 2.1 minus 2.1 is 0. We have 0 electronegativity difference. For HCl, hydrogen is 2.1, chlorine 3.0, so we have a difference of 0.9. So you get the idea here. We're just finding the difference between the 2 values. So A, according to our chart that we talked about before, was covalent. That's a purely covalent, a non-polar covalent compound because there is 0 electronegativity difference. B is polar covalent because it's greater than 0. There's obviously some sort of partial positive or partial negative charge within that compound. HNA would be a polar covalent compound again because there is some difference. And the same with HO. We see the same thing happening in those last 3. It's above 0 and less than 1.7, which is what would qualify it as an ionic compound. Which of the following molecules contain polar covalent bonds? Hydrogen fluoride is the only one that contains polar covalent bonds. In all of these compounds, we just have one element bound to itself, essentially, the same electronegativity value, so there's going to be zero difference. The only molecule where there is an electronegativity difference is hydrogen fluoride. So again, we're indicating which one is more polar, so what we're doing here is looking at the difference between the two. So for A, we see the value of the difference is 1.9. For HCl, we see it's 0.9. So the more polar bond is going to be the larger difference in each of these cases. For B, the larger difference is 0.9. For C, the larger difference is 0.9. And for D, the larger difference is 0.7. So that's how we would indicate the more polar bond in each pair. Write the Lewis structure for each of the following simple molecules. Show all bonding valence electron pairs as lines and non-bonding valence electron pairs as dots. The first one is pH3. We did this one in our notes yesterday. So phosphorus is in column 5, so it's going to contribute 5. Hydrogen is in 1, and there are 3 of them, so it will contribute a total of 8. We have phosphorus in the center, hydrogens around the outside. This used 6 electrons because each bond is 2, and then we had the lone pair on phosphorus. SF2, we have sulfur, fluorine on the outside. Remember, the more electronegative element goes on the outside. We have sulfur in column 6, fluorine in column 7 times 2. So this gives us a total of 20 valence electrons that we have to distribute. I'm going to put them around the outside first. 2, 4, 6, 8, 10, 12, and remember the 4 additional that we used for the bonds, that's 16 total, and then we have 18 and 20. So we've distributed all of our electrons here. HBr, hydrogen is in column 1, 1 electron in its valence shell. Bromine is in column 7, so again a total of 8. There's only one way to set these up, and that's to bind them to each other. We used 2 electrons to form the bond, so 8 minus 2, that gives me 6 left over. The only thing left to do is to put them around bromine in the form of lone pairs. CCl4, carbon is in column 4. Chlorine is in column 7, and there are 4. So this gives me a total of 32 electrons to distribute. I'm going to put carbon in the middle. I'm going to bond each of the chlorines around the outside. Just remember we talked about halogens going around the outside of a compound. I've used 8 electrons to do this. So 32 minus 8 gives me 24 to play with. Now I'm going to put them around the outside. So I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Nothing can go on carbon. Carbon already has access to 8 electrons. It already has its octet filled. The last homework question is more of the same, just maybe slightly more difficult compounds. We're still following the same process. So carbon is in column 4, 4 valence electrons times 2, and we're going to add that to hydrogen, which is in column 1, times 6. So this gives me 8 plus 6 equals 14 total electrons to distribute. Hydrogen always goes around the outside, so I'm going to put the carbons in the center, and then I'm going to put hydrogens all around the outside. This used a total of 2, 4, 6, 8, 10, 12, 14 electrons. So I've distributed all of my electrons just by bonding these elements together. For the next one, nitrogen is in column 5, fluorine is in column 7, and there are 3 of them. So adding these together, I get a total of 26. I'm going to put nitrogen in the center, and then fluorine around the outside. Remember, we like to keep the halogens around the outside of the compound. I used 6 electrons to bond them to each other, so this gives me a total of 20 left to use. So I'm going to start around the outside, 2, 4, 6, 8, 10, 12, 14, 16, 18, And the last two are going to go on nitrogen. I've distributed all of my 20 electrons. C4H10, carbon is in column 4. There are 4 of them. I'm going to add that to hydrogen's contribution of 1 times 10. So 4 times 4 is 16, plus 10 gives me 26 electrons to distribute. This is similar to A. I'm going to bond these carbons to each other. Then the only thing to do with hydrogen is to put them around the outside. Remember, hydrogen can only have access to 2 electrons, so I cannot put it in between 2 other elements. It can only ever go right around the outside. And in doing this, there's no other electrons to distribute anywhere. So I've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. And that would be an appropriate Lewis structure. SiCl4. Silicon is in column 4, and there's only one of them. Chlorine is in column 7, but there are 4, so this gives me a total of 32 electrons to distribute. Silicon in the center, chlorine around the outside. This took 8. I have 24 left. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24.